Okay, so here we are.
Hello, future people.
Today is chapter 10, which is the last chapter of part 1 of the book, which we're gonna have a very interesting conclusion. And the main topic for today is natural transformations. So it's kind of a funny
Actually,
thing because we have objects, and then from like there's an onion with many levels, and then we have the level 0, which are objects. Then level 1 is categories. And then we studied functors, which is like bridging the categories, mapping the objects and the morphisms. And now we're going to go to level 2, which is what about those mappings? Can we abstract them too? And the answer is yes. And this is the answer. Natural transformations.
it's all very natural. This will never stop being funny to me.
uh, so let's read this paragraph here. A functor embeds one category into another. It may collapse multiple things into one, but it never breaks connections. One way of thinking about it is that with a functor we are modeling one category inside another. I don't really buy this way of thinking about it though. To me it's not, that's very counterintuitive. To me functors are bridges. They are not embedding, the act of embedding.
Hmm.
Uh, there may be many ways of embedding one category into another, which is there may be more than one functor between two categories, right?
Yeah.
Sometimes they're equivalent, sometimes they're very different. And we're going to use natural transformations as a way to help us compare these different bridges, right? You may have different ways, so you can have a bridge that is very like plain, simple, like this. You have a bridge that does this, right? And you have a bridge that does like zigzagging and has some mountains going, like getting around mountains and stuff like that. How are we going to compare them? How are we going to compare them? So we have two functors f and g between categories C and D. If you focus in just one object A, in C it is mapped to two objects within D. That's important. F of A, and G of A. So here's the first of many diagrams you're going to see today. And not all of them are crazy because I think that 95% of them is fine. Uh, so here it is. We have an object A. They are going to within D. They are coming out of we are coming out of C, going to D, going to f of A and g of A. What if we want to go from f of A to g of A directly? We're going to call this alpha, the component alpha at A, right? And this is what it is, a natural transformation, right? So we are now making bridges between functors, not only categories. Well, we're going to discover later that a functor is also a category, but that's a spoiler alert.
I
So
mean,
this
we're
is,
gonna see it today, so it's
yeah,
not really that much of a spoiler.
yeah, but it's a spoiler of the future. And in a few minutes we're gonna get there. So we have this is the type signature, right? So it makes sense. Is there something going from here to here? Um, Something also important is this alpha A lives in D, right? That's also very important.
Yep.
Uh, so, functors not only map objects, but they also map morphisms. How we handle these cases with the natural transformation? It turns out that the mappings of morphisms is fixed. Under any natural transformation between f and g, f of f must be transformed into g of f. The mapping of morphisms by the two functors drastically restricts the choices we have in defining a natural transformation. Consider a morphism f from two objects A and B in C. It's mapped to two morphisms, right? So this is basically doing the lift process.
Yep.
So if you have a function f that goes from A to B, if you do f of f, you're going to have this, and if you do g of f, you're going to have this. We have seen this before. Right?
Right.
So the natural transformation A provides two additional morphisms that complete the diagram that you're gonna see down here, which is component alpha at A and component alpha at B, which is basically saying we are now at F at the image in D after crossing the F bridge, and we want to go to the location if you have taken the G bridge. So we are creating a new one. And this is how those bridges look like together. So we have A. If you take F, you're gonna go to B. If you apply capital F to F, you're gonna go to well, this is the conclusion. Let's do this later. So if you take A and you apply capital F, you're gonna go to F of A. If you take B and you apply F of B, you're gonna reach this point here in the middle. And the alphas, which are the yellow ones, they are creating this other connection to G of A, which is equivalent if you just applied G to A and G to B. Right, so here and here. You can get there from F now, from applied F before, capital F before, from both of them. So you have a component alpha at A and component alpha at B. So you're going to go to GA and GB. And also, if you have G of A and you do a lift of F, you can also go to G of B. So this is the diagram that we were working with. This is the diagram that we were working with.
It is very 3D.
Yeah, this is very 3D. So how can you tell it is 3D? Because there is some like dotted lines, such as this pink one. That's how you
That's
know.
f of f. Yep. Going
Now
down.
we have two ways of getting from F of A to G of B, right? So if you are here, you can take this route and then this route, or you can take this route and then this route. To make sure that they are equal, we must impose the neutrality condition that holds for any F. So these two paths, we want them to be the same. So this is how you write them. So you have component alpha at A. No, it's actually GF after component alpha at A and component alpha at
It
B
should be,
after F of F.
yeah, they need to be equivalent.
Yeah, so you're basically saying this coming after this needs to be the same as this coming after this, which, like, if you want a pictorial understanding, this is how you should read it. The neutrality condition is pretty stringent requirement. For instance, if the morphism f of f is invertible, neutrality determines component alpha at b in terms of component alpha of a. It transports component alpha of a along f, which is kind of weird. So if you get rid of the 3D and you just focus on these blue and yellow things and pink things, this makes sense. This makes sense. This makes sense, and this makes sense. But what we are saying is, what if the green one exists? So that's what you're saying. F of f is invertible. What does that changes in anything? That means that this guy needs to be equal to this after this after this.
Yeah, basically, if you start at f of b, if
Yes,
you, yeah, alpha of b should be the same thing as f
doing a
of
loop.
f minus 1. Yeah, it should be equivalent to going the long way around,
Exactly.
like
If
going up and
like
then right.
considering that this is the shortest path should give you the same destination as doing the longer one, which is from here to here to here. That's cool. That's very cool. So if there is more than one invertible morphism between two objects, all these transports have to agree. What does that mean? That means that if any of these is invertible and we have a two-way bridge that works going forward and going backwards, we need to make sure that this route needs to be equivalent to all of the other possible routes. right? But in general, morphisms are not invertible, but you can see that the existence of natural transformations between two functors is far from guaranteed. So the scarcity or the abundance of functors that are related by natural transformations may tell you a lot about the structure of the categories between which they operate. We're going to talk about this later on again when we talk about this lemma here. So looking at a natural transformation component-wise, one may say that it maps objects to morphisms. Because of the naturality condition, one may also say that it maps morphisms to commuting squares. There is one commuting naturality square in D for every morphism in C. So let's try to go through this paragraph again. One may say that it maps objects to morphisms. Why? Let's go over that. Uh, Maps objects to morphisms. Oh, it's because you're
Because
mapping
our
A to this morphism alpha component alpha at A, right?
yeah.
Yeah, I see. One may also say that it maps morphisms to commuting squares. So the commuting squares is because, well, you basically have
It's
some,
commuting because you can choose either path and you reach the same destination,
yeah.
and it's a square because, well, it's a square.
It's a square
And you are
because it's a
mapping
square.
A, and you are mapping A to this entire square, basically.
Yeah, yeah.
Not
Uh,
really A, you're mapping F from A to B, right, to the square.
yes, yes. This property of natural transformations come in very handy in a lot of stuff. Uh, Finally, natural transformations may be used to define isomorphisms of functors. Saying that two functors are naturally isomorphic is almost like saying that they are the same. Natural isomorphism is defined as a natural transformation whose components are all isomorphisms. So this is kind of a long shot. So natural isomorphism is defined as a natural transformation whose components are all isomorphisms. So you're basically saying that if this is an isomorphism, this is called a natural isomorphism as well then. And this also. Is that what you're saying?
It's if the natural transformation itself is an isomorphism, actually. Like if alpha is invertible for all points, then it's a natural isomorphism.
Okay, that's another way to put it. Sure. And now we're gonna go see some code to see how we're gonna make this into programming. So let's just start by having an object with type A. One functor
Remember this
f,
joint.
yeah, one functor f maps it to a type f of A. Another functor g maps it to g of A. The component of a natural transformation alpha at A is a function from f of A to g of A, in which both f and g are functors. So this would be the type signature of that. A natural transformation is a polymorphic function. So this is when you're using the explicit for all, but in Haskell this would be enough. Um, this is how you would do it in C++, right? Uh, this is how you do it in C++.
That's very noisy. That's very noisy.
Yeah, there's a lot of stuff going on here. Uh, yeah, but here we're gonna see a very important difference between how the way that, like semantical difference, not only syntax, on how C++ handles it and how Haskell handles the situation. So in Haskell, a polymorphic function must be defined uniformly for all types. For all types. It this thing must work across all of them, and you're even saying it in this other version for all of them. We're going to talk about it right now, and this is called parametric polymorphism. So on C++ uses ad hoc polymorphism, which means that you don't have to have something defined for all of them.
It can
Uh,
even be different for multiple types because
yeah.
in practice, parametricity means you can't actually look at the structure of the thing.
Yes.
Like
Exactly. Exactly.
which is not the case in C++. And funny enough, it's also not the case in Zig.
I see. Type checking is deferred, which unfortunately often leads to incomprehensible error messages. Uh,
We had some experience with that, right?
yeah, but this is important. Whether a template will work for a given type is decided at instantiation time, which I'm understanding it happens at runtime.
No, it's not runtime. It's when you actually use when you actually instantiate the polymorphic type to a concrete one. That's when the check happens.
Is when you instantiate what again?
Like when you instantiate the type variable into a concrete type, that's when the check happens.
Ah, I see, I see, I see. When you're making it like specialized, right?
Yes,
I see.
yes.
In C++, there's also a mechanism for function overloading and template specialization, which allows different definitions of the same function for different types, which is what Marin just said before. And then in Haskell, this is provided by type families and type classes. I haven't played a bunch with type families, so I'm hoping I'm gonna learn a little bit. Haskell parametric polymorphism has an unexpected consequence. Any polymorphic function of the type this is or if f and j are functors, which this is not saying, but you can make that restriction, this is a naturality condition. So here it is in categorical notation. Boom. In Haskell, the action of a functor g on a morphism f is implemented using fmap. I will first write in pseudo Haskell with explicit type annotations. So if you replace g with the fmap thing, you're going to get this out of this, right? And because of type inference, we don't have to have these other letters, so we can just write it like this. Although the fmaps on the right, the fmap on the left is not the same as the fmap on the right. Um, and you're gonna use this for equational reasoning. Um, what else? What else? What else? The the
And that
neutrality con
paragraph about
go on.
and
Go
that
on.
paragraph about containers, right at the beginning of the page. It's basically what we said, right? You're not allowed to pick inside of the
Mm-hmm.
type variables structure.
Yeah.
That's basically just putting it in another way.
Yes, exactly. So the naturality condition becomes a statement that it doesn't matter whether we modify the items first through the application of fmap and repack them later, or repack first and then modify the items in the new container. So let's actually read that again, but looking at the equational at this thing. I think it's going to be easier. It doesn't matter whether we modify the items first through the application of fmap. So we're talking first. So we're talking about doing this first and repack it later, which means doing alpha, or we repack it first and then modify the items in the new container. So this is basically saying if you repack it first and then do the fmap, it's the same as doing the fmap first and repacking it. That's basically what you're reading there. Um, let's see a few examples. So this is the safe head function is a natural transformation because it's mapping from the least functor to the maybe functor. And it works for any type, right? If you wanted to use the explicit for all, you could, but this can work for any type A. And we are not allowed to ask, oh, if A is specifically this, do this differently, which is what Marinho said, right? We cannot look into them, which is now it is the perfect time to reiterate that in Zig, we can, right? Because we can inspect the stuff here.
You can get the type info, right?
Yeah.
And do all sorts of stuff based on the concrete type.
Yes. Yes. Um, so now we're gonna do the equational reasoning using this instead of the alpha, and we're gonna see if this holds. We're gonna see that it does. And if we, yeah, this is the implementation of fmap of for lists, and this is for the maybe, and that's gonna work. So now it comes some unconventional ways of thinking about things. Because let's say that let's talk about the function length. Can we see it as a natural transformation? The answer is yes, but then you need to use the const functor. So you're basically mapping from list to const. And then we need to use this auxiliary function unconst, right? Which is basically doing unwrapping. But of course, this is just for like to be a little bit playful, because in practice you're gonna say this, you're gonna use this, right? You pick a list of any type and return an integer. Uh, and then we have the other
I
example, which is
mean,
the other way around. Can we go from const to something else? Go on, Manny.
I mean, this is equal up to isomorphism, so it checks out,
It is equal up to
right?
isomorphism. It is. But it is just kind of. This is the type of stuff that in educational terms makes sense to mention, but I wouldn't recommend for programming, right? And that, so
Yeah,
that's there's a reason we do it like this.
yeah, the top version, yes, you are closer to the theoretical foundation, but you're also adding a lot of noise.
Yeah, yeah. And what's important to understand is that this noise is not adding up, right? Because you may say, man, I can use safehead without ever understanding natural transformations, and you're right. But it is adding up because now I can see how this function semantically works in a different way, in a different perspective. Um, of course, I'm not saying that all of these different understandings have the same value, right? I would say that understanding what is a functor in categorical terms has more value than using the safe head as a natural transformation. But it is still you can see the connections, right? You can see how they are related. This thing, it is related, but the value is very very slim, very slim. Um, so the const functor is a little harder to see as like we're coming from there to something else. So we have this function here, right? Which basically does, well, it works, but it's kind of weird. And then we're going to go to the reader functor, right? Which is what we have seen before when we were talking about contravariant and stuff like that. We have showed that depending on which ones are coming here, we're going to have a covariant functor or a contravariant functor. If the A goes in the beginning and it is the second type parameter coming, it's going to be a contravariant functor. And if it is the output, it's going to be the covariant functor, right?
Yeah, here we're looking at the covariant one.
Yeah. And this is the functor implementation of this. And now it comes a little weird thing here. So for every type E, you can define a family of natural transformations from reader E to any other functor F. Right? We'll see later that the members of this family are always in one-to-one correspondence with the elements of F of A. And I don't know if I understand this sentence correctly. Uh,
Uh,
and then there's
for
an
instance,
example.
consider, yeah, let's look at the example. That's probably a bit better for intuition.
So consider the somewhat trivial unit type. The functor reader unit takes any type A and maps it into a function type unit to A. These are all just the functions that pick a single element from the set A. That's true. There are as many of these as there are of elements in A. Yes. Now let's consider the natural transformations from this functor to the maybe functor.
Oh, I
There.
think I see why. Because
Oh, I
normally
see, I
there
see,
would
I
be,
see. So the amount of natural transformations depend on how many instances of the
of the
destination functor,
yes, of the destination and also of the input, actually.
and also of the input. But in this case, unit has only one, so it's going to be only 1 times 2. Or that's an exponential thing. It's like 2 to the power of
No,
1
no,
or
no.
something.
It's because normally there are as many elements in a functor as the argument type, right?
Yeah.
But in this case, we're not actually using the arguments type directly. A we are using the inputs of the reader to populate the functor. So we're actually limited by the number of elements in the inputs type of the reader instead of the inputs type of the functor that you are going to.
That doesn't really make sense to me because we are limited because dumb and obvious we have only true because we can only go to nothing and just.
But the only reason that's the case is because, well, the only way to do a maybe unit is nothing or just units.
Sure. So it still seems to me that we are limited to the maybe even then.
We are. So instead, so the idea is normally the number of elements of maybe A is the number of elements of A plus one, right?
Yeah.
But in this case, we're not looking at the A, we're looking at the unit that's coming from the reader, you see? Because that's the input to the reader, which means that restricts how many values you can choose from the destination type based on the source type of the reader.
I agree with that. The fact that we have unit here instead of whatever, like integer, it makes sense that we are limited by that, but I don't see how we can run from being limited to from the destination as well. We need to.
We do. But the point is that it's not the A that's helping inform what's the final number of possible values. It's actually the unit, you
Yeah,
see?
no, the unit and the maybe. That's my understanding. The
The
A doesn't
unit and the
matter.
maybe. The A doesn't matter for the number of uh, potential constructions because, well,
Yes,
we're limited by the input type.
yes, yes. So I think I got it. These correspond to the two elements of maybe unit type, which, yeah, so both of them are participating on this limitation. And we're going to come back to this later on anyway. So beyond naturality. So now we're going to go back to the whole covariant and contravariant things. So imagine the contra. This is the contravariant one. This because the A is in the input position. So this is how you're going to implement that using again composition here. And you can write a polymorphic function from say op_bool to op_string. So it's going to work like this. So because these functors are not covariant, this is not a natural transformation in Haskell, which is set plus non-determinism and bottom. Uh,
Non-determinism.
yeah, non-termination and bottom.
Bottom and non-termination are effectively the same thing, though.
No, I know, but I'm just quoting the book um, from chapter 2 or something because I happened to read that again today. Not the entire chapter, but the Haskell category thing. And the way that I understood is that it's set plus non-termination and bottoms. Uh, but you're right, bottoms is the name that we also use for non-termination. Uh,
So it's not a natural transformation in Haskell, but it's a natural transformation in the opposite category, right?
yeah. Uh, so notice that the function f must go in the opposite direction than what we use with fmap because of the signature of contramap. Uh, yeah, and then it took me a while. Again, I looked at this and I said, wait a moment. We have a B going to an A, and then there's an A here and a B here. But then I got reminded, no, I need to rewrite these OPs things to the how they are supposed to be used. And then I noticed that, oh yeah, no, this actually makes sense. Okay. So are there any type constructors that are not functors, whether covariant and contravariant? Here's one example. So going from an A to an A. This is not a functor because the same type A is used for both the negative and in the positive positions. We can't implement fmap or contramap for this type. So then this will not fly.
Yeah, it's invariant actually, because it needs to be simultaneously contravariant and covariant,
Mm-hmm.
and yeah, that kind of restricts you too much. Fun fact, you also can't do it if you have a mutable cell, because a mutable cell, you can put stuff in it. So that would be contravariant, right? Because you need to pass it as an argument to actually put in inside of the mutable cell. But then you also want to read the cell later, so that's covariance because it's in a result
Yeah.
position.
Yes.
So
And now we're going to talk about if functors actually do form a category. And we're going to see that they do. So imagine that we have, there is a one category of functions for each pair of categories C and D. Objects in this category are functors. Again, so if functors are bridging categories, we are now assessing the bridges as we are looking at them as they are if they were objects, because they can be. Um, but the difference, and here's the plot, is that if the functors are the objects, we need morphisms. And what are those? Natural transformations. Um,
Amazing.
Now we're going to have to
Natural.
define composition of two natural transformations, but that's quite easy, right? So let's look again at some type signatures so to see how we can compose them. So imagine that we have a component alpha at A, which has this type signature. We would like to compose natural transformations, right? Because they are our morphisms on this level of the abstraction stack. So let's suppose we want to compose alpha with beta. And beta is this. And notice as well, we're using that interpretation that we are mapping objects to morphisms that we've seen before, that this is the same A. This is the same A.
This is the same A. It has to be.
Yeah. These morphisms are composable and their composition is another morphism. So we're basically going from f of A to h of A if you compose these things. We use these morphisms as the component of the natural transformation beta after alpha and the composition of the two natural transformations beta after alpha. So we're basically going to say that the compositions of the natural transformations is the natural transformation of their composition. And here is the diagram, which is not really that crazy, insane, because, and to me, I think the colors really help. So
They
if you
do.
have an alpha, an A, sorry, and you go to g of A, which is basically like a normal functor, you just apply the functor g. Same thing for f, same thing for A. We are now trying to understand, is there a relationship between these three? And the answer is, you can go from f of A to g of A using alpha of A. You can go from g of A to h of A using beta of A. And what we are trying to discover, well, what we already discovered and we are identifying is that there is the yellow, this outside yellow one, which is going directly from f of A to h of A.
Yep.
And then it comes this two-piece cake, which again, at first glance, it may be very confusing, but it's really not. So let's go over this. Again, we have an A. The only difference between this and this is that now we are introducing a normal function, which is f. That's why it got 3D. Because imagine, this is, if you look from the top on this cake, you're going to see that this top here, right? This top is this top here.
Yep.
And why it became 3D? Because now you're introducing B. So that's basically doing this. It's creating like the cake itself. If this was a pizza, this is now a cake.
We 3D printed a cake out of a pizza.
Yeah. That's funny. Uh, so let's go over this just for completeness. The top is exactly the same as this one. It's exactly the same. Removing these other way around. So it's basically the F, G, H, alpha of A, beta of A, which is what we have in here. Now, let's suppose that you have a B and you happen to have an F that goes from an A to a B. The same process will happen with B. So you're going to have an F of B, capital F of B, a G of B, and an H of B. We also have natural transformations between those functor destinations. So we have alpha of B, beta of B, and vertically, what's going to happen is the functor mapping the known capital F, which is going to be H of F, G of F, and F of F.
Let's call it small f.
Small f. And that's basically the image. And now finally, for each functor, there is an identity natural transformation 1f whose components are the identity morphisms. So it's basically going from you to yourself, which is the normal identity function.
Just specialized to a functor type, yeah.
Yeah. Um, and now we're going to go about a little bit of notation. Uh, because we're going to use different dots for different compositions, because this is where I started to get a little bit confused. So the dot for the kind of natural transformation composition I have described, the problem is that there are two ways of composing natural transformations. This one is called the vertical composition. Which one? Let's stop there.
The one
So
that we just saw, right? Where you just say, okay,
f of
I
a to
have a
h of a?
natural transform. Yeah,
Okay.
yeah.
So that's called vertical, because functors are usually stacked up vertically in the diagrams that they describe. But it's kind of isn't, man. Because from going to f of a to h of a, we are going horizontally. We're not doing a downwards arrow.
No, no, you're looking at the 3D version. Go up to the 2D one.
Yes.
You're
Oh,
going
okay.
down.
I see. I see. So this is why it's called vertical. Um, so we're gonna see what the heck it means to say they are horizontal composition. So the functor category between category C and D is written as this, right, with this exponential notation. Um, we started with a category, which is a collection of objects and morphisms. Categories themselves are objects in a higher level category cat. We've seen this before as well. Morphisms in that category are functors. We already seen this before as well. Nothing new. A home set in cat is a set of functors. Correct. For instance, cat CD is a set of functors between the two categories C and D. Nothing new until now. A functor category CD is also a set of functors between the two categories. A functor category is the set of functors. Its objects are the same as the members of cat CD. The same as the members. Uh, yes.
Yeah, because it's a functor
Yes.
category. The objects are
Yes.
functors.
Yes. Moreover, a functor category being a category must itself be an object of cat. Makes sense. We we have a relationship between a home set in a category and an object in the same category, which is kind of the same internal versus external thing that we have seen before in chapter what 9.
Yeah, yeah.
The situation is exactly like the exponential object that we've seen in the last section. Um, yeah, so now it's like bucket up because this you're gonna get maybe gonna get lost. Uh, in cat, well, we're gonna see how to construct the letter in cat, right? So we're gonna see how to construct this later this relationship that he's mentioning here. In order to construct an exponential, we need to first define a product. In cat, this turns out to be easy because small categories are sets of objects, and we know how to define Cartesian products of sets. We're gonna make pairs fundamentally. A morphism between two such pairs is a pair of morphisms, such as this. These pairs compose component-wise, and there is also an identity pair that is just a pair of identity morphisms. You also seen this before with the evolve thing. To make the long story short,
Yes.
cat is a full-blown category closed category, Cartesian closed category, in which there is an exponential object DC for any pair of categories. Okay, so let's take this little by little. Cat is a full-blown Cartesian closed category. What does that mean? Let's start
That
from
means
there.
you can make products,
So you have all the possible combinations of pairs of morphisms and pairs of objects,
basically.
in which there is an exponential object DC for any pair of categories. So now I think we need to go back to the exponential conversation. What would you say is the summary of an exponential, Marin?
It's basically a function. If you're a
Okay,
programmer, just think of it as a function.
okay. And by object in cat, I mean a category. So DC is a category which we can identify with the functor category between C and D. In cat, I mean a category. Yeah, because cat is the category of categories. So
Yep.
DC is a category which we can identify with the functor category between C and D. Yeah. So this is a lot. This is this is a lot. But take your time, take your digestion time.
It's not too different from what we've seen before. It's just the scale of things is larger.
Yeah, the scale is much larger. So now let's have a closer look. Functors between two objects have a richer structure in just a set. They form a category with natural transformations as morphisms. That's okay. Since functors are considered morphisms, natural transformations are morphisms between morphisms. That makes sense, right? Again, imagine the onion, and we are putting layers on top of it, and
Yeah,
and we are the upper level. We have natural transformations. So now we're gonna see a two category, which is it has a richer structure. So in the case of cat, seen as a two category, we have objects, small categories. So again, before when we were using sets to be our categories, the objects themselves they were inspectable. You could inspect them. You could see that they were numbers, they were strings, they were characters. Now we're grabbing that, closing it up, painting it black, and saying this is now the object. This is now the
amazing.
object. So the objects are categories now. One morphisms are functors between categories. Right? So this is normal functors. They are mappings that keep structure between categories, but they are mappings between one category and another one. These mappings can be also abstracted to be objects themselves. And the morphisms in that one are called two morphisms, in which they are natural transformations.
Between functors. Yeah, this is like it's putting the meta in programming in some sense.
Yeah, this is definitely putting the meta word in programming. So instead of a home set between two categories, we have a home category, the functor category DC. We have regular functor composition, which is a functor f from DC composed to a functor G in ED, and you can go from C to E. But you also have the composition inside each home category, vertical composition of natural transformations or two morphisms between functors. So when you compose natural transformations, this is called vertical composition. Is that it?
Yes, because you're basically saying, okay, we're going to treat a natural transformation as just, a morphism. We're going to put the tail of one at the head of the other, and that's just normal composition as we've seen so far.
Yes. No, wait. I think we said different things, or I got distracted. I'm gonna try to repeat and see if that's what you said. If you're composing natural transformations, that's vertical, and if you're composing F maps, that's horizontal.
Pretty much.
Okay. Okay.
Yeah, we're going to see that in more detail I think it's the next page or two. But yeah,
And now that's the question: how do they interact? How these two types of composition? How do they interact among each other?
I
So
mean, you
let
can call them types because there's a line coming up that had me scratching my head for a moment, and then I realized, oh, this has to do with type theory.
that's good. So let's pick two functors or one morphisms. So I'm going to C from C to D and D to E. Right? So this is a normal functor. So if you compose them, this is basically composing F maps. Suppose we have two natural transformations, alpha and beta, that act on functors F and G. So you're going from functor F. So here's the important difference. C, D, and E, they are categories. F and G here, they are functors. Don't don't get yourself confused.
Yeah.
Uh, so here's how that works. So C, D, and E, they are categories. Again, the categories are now our objects. So that's why it's important to be comfortable not inspecting them. So the functors allow us to bridge them together with horizontal composition. And these vertical red arrows here, this is the natural transformations. And this is what we call vertical composition.
Oh, actually, to be more precise, You speak of horizontal composition of natural transformation, not functors, because there's only one way to compose functors, which is like what we've seen so far.
Wait, I think you said horizontal by mistake. Didn't you mean
No, I
vertical?
didn't. No, I didn't. We speak of horizontal composition of natural transformations, not of functors, actually.
No, but it's not horizontal, or am I understanding things wrong? It's vertical.
Vertical is the one where you say, okay, I have a natural transformation and another one, and I'm going to put the output of one as the input of the next. That's not quite what's happening here. Here, the natural transformations are alpha and beta. You're not
Hmm.
gluing the tail of
Oh
alpha
no, you are
to
not.
the
You're.
head
Oh,
of
sorry
beta.
then. I understand. I said it wrong. You are not in this specific drawing here, diagram. You are not composing alpha and beta. But we've seen this before in the previous pages. That's what
I
I meant to
mean,
say.
in some sense, you kind of are, but not really.
Yeah. Notice you cannot apply vertical composition to this pair because the target of alpha is different from the source of beta. You can just look at the types. This is F prime is not G. Then you're done. In fact, they are members of two different functors categories. We can, however, apply composition to the functors f prime and g prime because the target of f prime is the source of g prime. It's the category D. So what you're saying is you can compose things going from f prime to g prime.
Yeah, just
So
as you
there's an arrow
can going
here.
from F to Z. Yeah,
Yeah, which is this one. No. Uh, okay, we're gonna have to go over this a little bit, but anyway. So what's the relationship between the functors g prime after f prime and g and after f? Having alpha and beta at our disposal, we can define a natural transformation from those. Here's the sketch, right? So once again, go a little by little, go a little by little. So if you have a and you apply f, you go to f of a. If you have a and you have f prime, you go to f prime of a. That's fine. Suppose you have a natural transformation going from f of a to f prime of a. Then you have g, which is gonna, well, which is another functor. So you're basically just like wrapping g on top of the stuff. So g f of a, here you're gonna have g prime f of a, and here you're gonna have g prime f prime of a, and you're also gonna have g f prime of a. So all the possible combinations. So this is why we have so many points in here. And the
yeah, and
question
we're
is,
trying
can
to
we go from this point here to this one down here?
yeah, we're trying to define that diagonal there, basically.
Yeah. So you want to see if there's a connection between g f of a and g prime f prime of a, right? So it's basically explaining all of that. Um, so that's a lot of morphisms, but it should make sense. This is not that hard. It's just a matter of writing that down.
It's geometry, basically.
Yeah. So our goal is to find a morphism that goes from g f a to g prime f prime a, which is this dotted one, not colored.
The diagonal, yes.
Yeah. Um, in fact, there's not one but two paths we can take. Right? So what are those paths? We can go from to here and then to here, or we can go to here and then to here. Right?
Yes.
If you write that down, if you write that down, you're gonna see that those are the two candidates. But because of the naturality for beta, we know that they are equal. Uh, and now we're gonna call this. That's now here's the naming. We call this natural transformation the horizontal composition of alpha and beta. So the beta after alpha is something that goes from the composition of G and F to the composition G prime and F with F prime. So that's what it means, and see that a little bit more clearly maybe. You need to look at a cat sideways, which is a little strange visual pictorial thing. So look at natural transformations not as arrows between functors, but as arrows between categories. A natural transformation sits between two categories, the ones that are connected by the functors it transforms. We can think of it as connecting these two categories. So if you have a category C and a D, you have two functors and an alpha connecting the functors. You can think that you're connecting the two categories using alpha horizontally. I don't like this though, because I think it's kind of misleading. It's kind of misleading.
It
Because
kind of is. I mean,
you are not really connecting C and D. You're connecting their functors, which is a completely different abstraction.
yeah. And actually, I think the line that I had to think about for a moment is coming up, and that is related to this actually. So yeah, it's the paragraph. We also have an identity arrow going from C to C. It's the identity natural transformation that maps the identity functor on C to itself. Notice that the identity for horizontal composition is also the identity for vertical composition, but not vice versa.
Okay, I don't know if I got it. Uh,
Yeah, I had to think about that for a moment. I'm still not 100% sure, but it has to do with how the type variables get instantiated. My intuition tells me that the reason the identity is valid for one case but not the other, or rather, the reason that you can use one identity for both cases, but the other identity only for one is because the identity for vertical composition is actually it should be less polymorphic actually, because then
Wait a moment before you continue. Let's try to go over again. And because I don't know if I understand it, maybe you can try to help me, and maybe you're gonna figure out yourself as well. Okay. So let's focus on two objects of cat, category C and D. That's fine. There is a set of natural transformations that go between functors that connect C and D. That's also fine. We have a bunch of alphas, basically. We have a bunch of them. These natural transformations are new arrows from C to D, which again is this image that I don't really agree with. By the same token, there are natural transformations going between functors that connect D to E, which we can treat as new arrows going from D to E as well. So basically there is an imaginary E here with, I don't know, beta, and the horizontal composition is the composition of those ones, so composing alpha and beta, which is exactly what we are interested in. Um, we also have an identity arrow going from C to C, so there is an arrow going from C to C. It's the identity natural transformation that maps the identity functor on C to itself. So it's basically f of a going to f of a, right?
yeah,
Cool. Notice that the identity for horizontal composition is also the identity for vertical.
not vice versa.
Wait a moment.
Yeah, if you try to,
Wait a moment.
yeah, that not vice versa is what had me thinking for a while.
No, 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 but I'm trying to go before the vice versa. So the identity for horizontal composition is also the identity for vertical. Is it saying that the identity meaning f of a going to f of a is the same for both?
Uh, yes.
But how not vice versa? That's
Type variable. There's a type variable way in the middle there.
that's how not vice versa?
Because if you instantiate the variable to something which may still be polymorphic, suddenly you have another type, a secondary type, which is more specific.
Man, I think you're gonna have to write that down because I'm not really following how not vice versa. Maybe what I'm saying is wrong. It's not f of a to f of a then. It needs to be something else.
So we have an identity arrow from C to C. It's the natural transformation that maps the identity functor on C to itself. Okay, so So let's start with identity functor, okay? Because that's the object of the morphism, which is the natural transformation, right? So an identity functor, um, the identity functor, which maps C to itself, would basically be ID of f of a to f of a. Um, yeah, so it would be basically something like this, right? So
Yeah,
I wrote the
f of
type
a
here.
to f of a. Right.
Yes, but uh,
And that's for both of them.
or
That is for both of them, right? Both for horizontal and vertical.
yeah, I have a feeling that this actually is a bit backwards because here's the thing. What if A is itself a functor, right?
Yeah, that it seems to me that what we are going for here. What if a is another thing? Is
And so
another
if
functor.
A is, let's put G after F actually, because that's what's in the diagram. Yeah, so let's let's forget for a second that in Haskell, uppercase are concrete types. Let's say that G and F here are type variables, okay, even though they are uppercase.
Okay, that's fine.
You can specialize the identity on the top to the one on the bottom, right? If you say, okay, F is actually G, and then the A is to an F of A where F is a different variable, but you can't go backwards because
Yeah,
the
man.
type
I
on
don't.
the bottom is more because the type where on the bottom is actually more specific than the one on the top. Actually, let me just rewrite the variable there to make it a bit clearer. Of a renaming for the win.
Oh, for renaming. So if you have g of a, my identity being g of a going to g of a, and then that a could be f of b. Which one is which? So is the first one? Uh,
Yeah, and that's what has me slightly confused because, well, let's talk about the type of a vertical composition, right? You would go from a G of A to an F of A, or vice versa. Doesn't
yes.
matter because
Yes.
variables. That means that the A is abstract in both cases.
Yes.
But but if you have a composition of functors, so like uh, G and F being functors, right? So that means that actually the A that was abstract is actually now a functor type. So
Hmm. Okay, so let's do the following. We have 2 minutes left. Let's go back to this and maybe write that down so then everybody can follow.
yeah, we
Um,
should do that.
yeah, because this is kind of tricky. This is kind of tricky. But to me, although I don't understand this completely, I think I understand horizontal composition and vertical. The vertical one is composition of F maps, and the horizontal one is composition of natural transformations.
Uh, you are composing natural transformations in both cases. Just that in this case,
No, I don't think we are. I don't. I really don't think we are. Let's go back for me to explain my understanding. So, uh, if you have an f of a and a g of a, right? You
yeah,
can and an h of a, and an h of a. This is you said it's doing vertical composition, right? This
yes,
this is doing vertical. So yeah, then I think I was wrong. Then you're right. We are both dealing with natural transformations in both of them.
yes,
So if you compose fg to an h to go f to h, this is called vertical.
Yes.
Horizontal now seems tough because it doesn't really make sense.
Horizontal, you can think of it as like instead of having two functors that are just loose by themselves and you are moving between them, horizontal means okay, you have two functors that are already pre-composed, and now you are moving to another functor which is based on that pre-composed starting point.
Yeah, that doesn't follow to me at all. That doesn't follow to me at all. But I thought I got it. I thought the vertical was about composing math maps and horizontal about composing natural transformations, but I was wrong. Both of them deal with natural transformations. But what is the difference then? What is the
The difference is that
difference?
uh, in the vertical case, you're just going from one plane functor to another. Okay?
Oh, wait a moment. I think I understood what you said before about the pre-composed. So vertical, the functors are the objects and you are traversing them. Horizontal, their compositions are the objects and you're traversing those.
Yes.
Okay, so there is actually more layers to this onion then,
Yeah,
because
some layers are sideways.
that's crazy.
Yeah, this is a very non-Euclidean onion. It's kind of weird.
because because if you I wouldn't say it's a non-Euclidean, but because if you think about it, if you have a functor and you are this is a functor and this is another functor, their composition we call this vertical for some reason. But if there is a composition, so going from here to down here, so this, there's a big arrow doing that. If you compose, if you treat that composition as an object, and you want to go to another composition, such as this, for actually now geometrically makes sense because if this is vertical, the big arrow and the other big arrow would be doing this, like in
Yeah.
a it would be like 3D rule of like this or whatever I saw in university. So yeah, so I understand the horizontal. Wow. So I got it completely wrong before. Okay, but now I understand. Now I actually understand.
Yeah, there's a lot of depth in this topic.
So finally, the two
You have
compositions satisfy the interchange law. So if you have compositions of uh, oh wait, we're
the
gonna
dots are
the dots
the dots are
matter.
vertical.
Yeah, but the dots
Yeah, the
the
dots are
dots matter.
vertical.
Wait, which one is the horizontal? The big one.
The big one is the horizontal, yes.
So
You can tell because you
if
are mapping composition. Well, I guess
if you
mapping
have
composition in
two
either
big,
case.
so the little dot, let's call it the little dot. The little dot is the vertical composition, right?
Yes.
So composing this with this and then doing that, it's the same as doing that and then this. Yes, yes, yes. Okay, I see. That's crazy.
I will
uh,
quote Saunders MacLean here. The reader may enjoy writing down the evidence diagrams needed to prove these facts.
uh, use a functor using
Yeah.
natural transformation. We can, however, interpret the functor error as a special kind of natural transformation. Reinterpret the functor arrow. Which arrow now we are talking?
Um, the functor arrow, the arrow from category to category, basically.
We can, however, reinterpret the functor arrow as a special kind of natural transformation, the identity natural transformation acting on this functor. Uh,
That's basically like saying, okay, I'm going to interpret the number 3 as actually being the identity function specialized to work only on the number 3, which is a bit weird, but it works.
okay. So you often see this notation, where f is a functor and alpha is a natural transformation between two functors going from C to D. Since you can compose a functor with a natural transformation, this is interpreted as an horizontal composition of the identity transformation. Yeah. Yeah, I don't think I can grasp completely what this means. Since you can compose a functor with a natural transformation, this is interpreted as a horizontal composition of the identity.
Yeah, that basically means, okay, if you see someone saying, okay, I'm composing a functor with a natural transformation,
Yeah.
you can actually interpret that as, okay, I'm actually composing a natural transformation with another natural transformation, but that second one is actually the identity natural transformation specialized to a particular functor.
So it's basically useless then. You could just say alpha.
No, I mean, it is not useless because this is horizontal composition. So,
No, but it's just you just know that because it's using the big dot, right?
yes.
Yeah,
But it's
I
also
would
not
never
useless
do that
because
though. This is very misleading. Because if this is basically saying I'm composing this with the identity specialized to this, why not just say this then?
then you are being more polymorphic than you perhaps may intend to be.
Ah, okay, you're right. You're right. If I want to be less, that's true. Jeez, okay, okay. So now here's the conclusion. Here's the conclusion. A set of morphisms turns into a function object. Um, a set of morphisms turns into a function object. As an object, it can be source or a target of another morphism. So that's the idea behind higher order functions. That makes sense. A functor map objects to objects, so we can use it as a type constructor or a parametric type. A functor also maps morphisms, so it has a higher order function called fmap. There are some simple functors like const, product, coproduct that can be used to generate a large variety of algebraic data types. Function types are also functorial, both covariant and contravariant, and can be used to extend algebraic data types. So functors may be looked upon as objects in the functor category. So now the functors themselves become objects. As such, they become sources and targets of morphisms, which has a special name called natural transformations. A natural transformation is a special type of polymorphic function. And that's the conclusion. Right? So we are a little bit above 1 hour uh, in time. But I think aside from the whole identity, yeah, aside from this statement,
Yeah, I still have a feeling this is kind of backwards. I would think that vertical would work for horizontal, but not vice versa, because vertical is actually the more general type,
yeah,
the
right?
identity for vertical
Yeah,
composition.
that makes sense. What you said makes total sense. But you're gonna have to think more about that. So what I'm gonna have to do, I'm gonna have to read this later part again because now that I think I understand the difference between horizontal, because now that I did the whole imagery on my mind on what arrows are becoming which ones, and
And
then
with your hands as well.
yeah. And what you said before about the pre-composed that helped to figure out what we are talking about. So there are 3 layers then. That's kind of weird.
And one layer is sideways.
Yeah. So the okay, okay. So I'm gonna finish the recording now.
Bye bye.